Hi and welcome to this tutorial about the monkey and the shark. Actually it's about carbonyls, isn't this one? Have I ever told you the story about the monkey and the shark? Well, once upon a time there was a monkey who absolutely loved carbonyl groups, and he was happy swinging on one of the carbons of the carbonyl functionality when all of a sudden comes this shark out of the water and the monkey's gone. "But you can't defeat me," said the monkey, "because I've got a carbonyl group with a polar bond." "What's a polar bond?" the shark said. "Well, let me tell you." Okay, that's enough of the monkey. So let's have a look at this polar bond. The electronegativity of the oxygen actually draws more electron density, if you will, towards itself. So the little red balloon bubble around the carbonyl group there that I've drawn is trying to just indicate that slightly. We use this little symbol delta. It's a Greek letter for D, meaning partial charge, if you will. So it's not a full charge. It's not all the electrons don't rest on that oxygen. It just means that part of it does, and that's just like a balloon. It's got a different shape. Most of the electron density lies on oxygen because the electronegativity is as simple as that. So what does that mean? Why does it become such an important functional group? Well, if we wanted to attack this molecule, then we're either going to attack it with a neutral species using a pair of lone pair of electrons, or we're going to attack it with a charged species, and if it's a nucleophile then it's got a negative charge and it's going to attack with a pair of electrons, or we're going to attack it with a positively charged species such as a proton for an acid. And now we've got a place where we can attack it. We've got the carbon, which is positively charged, and we've got the oxygen, which is negatively charged. If we attack it with the nucleophile I've shown here, then it will attack the carbon, because that's now delta positive. That's partially positively charged. So what will happen is effectively the nucleophile will transfer its electrons onto this new molecule of the carbonyl, and the electrons will then transfer onto the electronegative oxygen to give you an intermediate species as shown here. Now if this reaction is worked up with a bit of acid, you'll have effectively converted the carbonyl into a new species which has now got an OH on it rather than a carbon double bond, and that is of course an alcohol as shown here. So that's a basic introduction to the carbonyl group. Right, and before we go, we just have a few closing notes on the nucleophile itself. The nucleophile can be a variety of reagents. So here we've got R-, which represents an alkyl group, and we've got ethyl here as an example. That R- can come from a variety of reagents which you can commercially buy, or you can make them as well in the laboratory. And examples would be a Grignard reagent, organolithium reagent, or even organocuprates and stuff like that. Another familiar one which will be talked about in class is reducing agents such as lithium aluminium hydride, the sodium borohydride. There's many borohydride reagents you can use. They're a really good source of H-, which is the hydride ion, and when you reduce across that double bond with the hydride source, you will end up with an alcohol. Reduce a ketone, you get ketone, you get a secondary alcohol, and reduce an aldehyde, you get primary alcohol, and we'll cover them in the next tutorial. So the take-home message is never trust a monkey, especially if it's got a carbonyl group in its hand. That's it for now. Bye for now.